do something with me for a second. Look at your own hand. Look at whatever's in front of you. A mug, a wall, the light in the room. Look up tonight and find a star. Every one of those things, from your fingernail to that star, is made of the same handful of stuff, the same protons and neutrons and electrons you meet in first-year chemistry. It's everything anyone has ever seen or touched or held. And here's the sentence that has kept me up at night. If you gathered up all of it, every atom that has ever caught the light, in every star and planet and living thing, you'd have a thin skin stretched over something enormous and dark. The overwhelming rest of the universe is two things nobody has ever seen or held or named. One holds the galaxies together. The other is pulling the whole universe apart faster and faster as we speak. We have weighed the cosmos carefully, and we recognize almost none of what's on the scale.
And I want to sit in that with you rather than rush past it, because it is genuinely one of the strangest facts in all of science. We are not talking about some far corner of the universe we haven't gotten to yet. We're talking about here, the space your hand is moving through right now. It's full of something. We can measure how much of it there is extremely precisely, and we cannot tell you what it is. That gap between how well we can weigh it and how little we understand it is the whole episode. I'll try to be honest at every step about which side of that gap we're standing on.
Okay, but before you scare me with the 95%, I need to stand on ground I've actually walked on, because when you say a galaxy is being held together by something invisible, my very first instinct, the annoyed undergrad instinct, is, hold on, this is just circular orbits, right? Can we start from a problem I've actually done for homework?
That is exactly where this whole discovery started, historically and logically. So yes, let's start on your homework. Just circular orbits, right?
Then let me say the thing out loud, and you tell me if I'm being naive. A star going around the center of a galaxy is just a thing on a circular orbit. And a thing on a circular orbit is one equation I know cold. V squared equals gm over r. The speed depends on the mass pulling you in and how far out you are. That's it. That's the harmonic oscillator level fact of orbital mechanics.
It is not naive at all. It's the right first move, and you've written down the exact tool the discovery is built on. Let me just make sure we both hear where that equation comes from, because the whole story lives inside it. For anything on a circular orbit, there's a balance. Gravity pulls you inward, and to go in a circle instead of flying off in a straight line, you need exactly that much inward pull, the centripetal requirement. Set the gravitational pull equal to what a circle demands, and the mass of the orbiting thing cancels right out, and you're left with your equation. The speed squared equals big G, Newton's constant, times the mass pulling you in, divided by your distance from it.
Right, and the thing I always underline is that the only mass that matters is the mass inside your orbit. The stuff farther out than you doesn't pull you anywhere on net, so the speed is set by how much mass is sitting inside the circle you're tracing.
You just said the single most important sentence in this episode, and we're going to come back and stand on it. The speed is set by the mass enclosed inside your orbit. Hold that. Now, let's take it for a walk in the one place you know it works perfectly. The solar system.
Okay, in the solar system, basically all the mass is the sun, sitting right in the middle. The planets themselves barely count. So the mass inside any planet's orbit is just the sun. Same number for all of them.
Same number for all of them. So in your equation, the mass on top is fixed. It's always just the sun. And the only thing that changes as you go from planet to planet is the distance, r. So what happens to the speed as you move outward?
If the mass is fixed and only r grows, then v squared goes as 1 over r, so the speed itself falls off as 1 over the square root of the distance. Farther out means slower. Mercury, right up next to the Sun, is whipping around fast. Neptune, way out in the cold, is just crawling.
Mercury races, Neptune crawls, and every planet in between falls neatly on that curve. Speed dropping as you go out, exactly like 1 over the square root of the distance. This is Kepler. You've plotted it. It works to spectacular precision. It's one of the great triumphs of Newton. So now, with total confidence, let's walk out into a galaxy and expect the same thing. The star that won't slow down. Picture a spiral galaxy, one of those beautiful pinwheels. Where's the light?
Piled up in the middle. There's a bright bulge in the center, and then the spiral arms, and it all fades out as you go toward the edge. By the time you're way out past the visible disk, there's almost nothing to see.
So here's the natural assumption, the one everybody made, and it's a completely reasonable one. Assume the mass is where the light is. The stars are the stuff is what gravitates, and the stars thin out as you go out. So once you get past that bright central region, you have enclosed nearly all the mass of the galaxy. There's almost nothing further in your circle to add.
Oh, I see exactly where this is going, and I can do it myself. If I'm way out past the bright part, then the mass inside my orbit has basically stopped growing. I've already scooped up almost all the stars. So now I'm in the same situation as Neptune. Fixed mass on top, and I just keep increasing r. So the orbital speed of a star way out at the edge should fall off, 1 over the square root of the distance. Just like the planets. Stars near the center go fast, stars out at the rim go slow.
That is precisely, exactly the prediction. And it is so clean and so obviously correct that it barely feels worth checking. It's just Kepler again, scaled up. Now, the measurement. How do you even measure the orbital speed of gas and stars way out at the faint edge of a galaxy, where you can barely see anything?
Doppler shift, I'd guess. The same thing that makes a siren drop in pitch as it goes past. Stuff coming toward you has its light shifted a little bluer. Stuff going away shifts a little redder. And how big that shift is tells you how fast it's moving.
Exactly that. You take the light, and crucially, you can use the glow of hydrogen gas, which reaches out much farther than the bright stars do, and you read its speed straight off the shift in its colors. So a woman named Vera Rubin, working with an instrument builder named Kent Ford, sets out to do this carefully, galaxy by galaxy, tracing the speed of the gas from the bright center out into the dark edges. She's expecting your curve, the falling curve, fast in the middle, slowing down as you go out.
And I'm guessing from the way you've set this up that she did not get my curve.
She got a flat line. You go out from the center and the speed climbs a bit, and then it just levels off and stays. Out and out and out, past the bright disk, way out into the region where there's essentially no starlight at all. The gas keeps orbiting at the same speed. It does not slow down. The curve refuses to fall. The star at the edge is moving just as fast as one much closer in.
Wait, let me make sure I feel how wrong that is. The planets slow down as you go out. That's not a fragile little effect. That's Kepler. That's rock solid. And a galaxy just doesn't. It flatly ignores the thing my textbook is built on.
It flatly ignores it. And now, this is the whole episode right here, so let's do it slowly. Let's turn your own equation around on it. You told me the speed depends on the mass enclosed and the distance. Now nature is telling us the speed is staying constant while the distance keeps growing. So look at v squared equals gm over r, but treat the speed as fixed and ask, what does the enclosed mass have to be doing?
Okay, if v squared is constant, held fixed, and it equals g times the enclosed mass divided by r, then the enclosed mass divided by r also has to stay constant. So the mass enclosed, call it m of r, the mass inside radius r, has to grow right in step with r. Double the radius, double the enclosed mass. Triple the radius, triple the mass. It just keeps climbing.
There it is. That's the discovery, and you just derived it with one equation from your first mechanics course. A flat rotation curve means the enclosed mass keeps growing, straight line, as you go outward. But go back to what you're looking at through the telescope. Out there, past the bright disk, how much starlight is there?
Almost none. That's the whole point. I'm way out past where the galaxy shines. So the mass keeps piling up in a region where there's basically nothing to see. There's more and more stuff enclosed, and it's dark.
There's more and more stuff, and it's dark. So the galaxy you see, the bright, gorgeous pinwheel, is sitting inside something far bigger that you cannot see at all. A vast, roughly spherical cloud of unseen mass, dwarfing the luminous galaxy tucked in its middle. People call it the dark halo, and the only reason we know it's there is that the stars at the edge are moving too fast for the light alone to hold them. They'd fly off, the galaxy would come apart, unless there's a great deal of extra mass out there gripping them gravitationally.
Can I try an analogy, and you tell me if it's a bad one? It's like the visible galaxy is a small bright thing hanging inside a much larger invisible skeleton, a scaffolding, and the scaffold is what actually holds the shape.
It's a useful picture, and I want to let you keep it. But let me put the fence around it, because a picture that quietly turns into a false claim is how people get fooled. Scaffolding makes it sound rigid, like girders, like it has structure and edges you could knock on. It's nothing like that. It's a diffuse, smooth cloud of some kind of stuff, and it makes itself known in exactly one way, through its gravity. That's it. It doesn't glow, it doesn't block light, it doesn't feel solid. So keep the idea that the bright galaxy hangs inside something much bigger. Just drop the girders. It's a haze of gravity, not a frame.
Fair. So this is one galaxy, Rubin's galaxy. My cynical side says maybe that one's just weird. One strange galaxy is a curiosity, not a revolution.
Your cynical side is doing its job, and it's exactly the objection the field had. So Rubin and Ford didn't stop at one. Through the 1970s and into the 80s, they did galaxy after galaxy. Their landmark survey covered 21 spiral galaxies, and the flat curve was there every single time. It wasn't a quirk of one oddball. It was the rule. Essentially, every spiral galaxy is doing this. That's what turned a curiosity into something the entire field was forced to explain. And here's a detail I love. This wasn't even the first whisper of it. 3 witnesses who never met. Decades before Rubin, back in the 1930s, an astronomer named Fritz Zwicky looked at a big cluster of galaxies, a swarm of them, all buzzing around each other, and he measured how fast they were moving. And they were moving so fast that the gravity of everything he could see, all the visible galaxies, came nowhere near enough to hold the swarm together. By his reckoning, there had to be something like 10 times more mass there than met the eye, or the whole cluster should have flung itself apart long ago. He even coined a name for the missing stuff, in German, dunkle Materie, dark matter.
So somebody had basically shouted, "There's missing mass," decades before Rubin, and I've never heard his name. What happened?
He got more or less ignored for a generation. It was one strange result about one cluster. The measurements were hard, and the idea was easy to file under probably some error we'll sort out later. It took Rubin and Ford's flat curves, clean, repeatable, galaxy after galaxy, to make it undeniable. And that's the first of what I think of as 3 independent witnesses. 3 completely different ways of looking, by different people, at different scales, that all point to the same missing mass. Witness 1 is what we just did, the rotation curves. Witness 2 is my favorite, because it's the one where you almost catch the dark matter in the act. Caught in a collision. There's an object called the bullet cluster. It's actually two clusters of galaxies, billions of light years away, that have crashed straight through each other. A colossal collision still in progress. And a collision is the perfect trap for pulling the visible and the invisible apart, so you can see they're two different things.
Okay, walk me through it, because you can see two invisible things separate. Sounds like a contradiction.
Fair. Here's the key fact most people don't know. In a cluster of galaxies, the ordinary matter, the normal atoms, is mostly not in the galaxies themselves. Most of it is in a vast cloud of hot gas spread between the galaxies, so hot it glows in X-rays. So to find where the ordinary matter is, you don't count galaxies. You point an X-ray telescope, the one used here was Chandra, and map that glowing gas.
Got it. So the X-rays show you where the ordinary matter sits, and then you need some separate way to find where the total mass is, including any invisible mass.
Exactly. And there's a beautiful independent way to do that. Gravitational lensing. Mass bends the path of light, so the light from far-off galaxies behind the cluster gets distorted as it passes through. And from how those images are warped, you can map where the mass is, all of it, seen or unseen, whatever it's made of. So now you have two independent maps, one from X-rays showing the ordinary matter, one from lensing showing all the mass. In a normal, undisturbed cluster, those two maps sit right on top of each other, and you learn nothing. But this cluster just had a head-on collision.
And I bet the collision does something different to the two kinds of stuff.
It does, and here's the whole thing. When the two clusters passed through each other, the two clouds of hot gas, the ordinary matter, ran into each other. Gas is like that. It collides, it drags, it piles up and slows down. So the gas got stuck in the middle, lagging behind. But the other mass, whatever the invisible stuff is, sailed straight through, barely touched, and kept going. So when you lay the two maps side by side, they've come apart. The lensing map, where most of the mass is, has moved on ahead, cleanly separated from the X-ray gas left behind in the middle.
Oh, that's gorgeous. The mass and the ordinary matter are literally in different places on the sky, so the mass can't be the ordinary matter. You can see them sitting apart.
You can see them sitting apart. Most of the mass is somewhere the ordinary matter isn't. That's about as direct as this evidence gets. It's why the paper that reported it used the phrase, a direct empirical proof. Now let me hand you the analogy and its limit in the same breath, because this one gets abused. People say the dark matter passed through like a ghost through walls. Fine, but a ghost is magic and this isn't. The reason the invisible stuff sailed through is mundane and specific. It barely interacts with anything, even with itself, except through gravity. The gas got stuck because ordinary matter feels pressure. It shocks, it piles up, it drags. The dark stuff feels none of that, so nothing slowed it down. The collision didn't reveal a ghost. It revealed a difference, one kind of stuff that bumps and one kind that doesn't. And that difference is the point.
So that's two witnesses, the rotation curves and the collision. And they've got nothing to do with each other. Different scales, different methods, different people.
Nothing to do with each other, same answer. And the third witness is the strangest of all, because it's a photograph of the universe when it was a baby. The baby picture of the cosmos. If you look out in every direction with the right kind of telescope, you find a faint glow filling the entire sky, a bath of microwaves coming from all around us. It's the leftover heat from the young universe, released when the cosmos had cooled just enough to become transparent, long before there were any stars or galaxies. It's the oldest light there is. We call it the cosmic microwave background, and a satellite called Planck mapped it in exquisite detail.
I've heard of it, the afterglow of the Big Bang. But how does a picture of the baby universe weigh the dark matter? That feels like a huge leap from Doppler shifts and colliding clusters.
It is a huge leap, and that's exactly why it's such powerful confirmation. Completely different physics. So gently, that baby universe wasn't perfectly smooth. It had tiny ripples in it, slightly denser spots and slightly emptier spots, and those ripples were sloshing like sound waves in the hot, early gas. Now here's the trick. Ordinary matter and dark matter behave differently in that sloshing. Ordinary matter feels pressure. It pushes back, it bounces. Dark matter doesn't. It only gravitates. It just sits there and pulls. So the two kinds of stuff leave different fingerprints in the pattern of ripples. And that means when you measure the pattern precisely, you can weigh the two separately. How much ordinary matter, how much dark matter, from a completely independent direction.
So this is the third, independent scale reading, and it gives you actual numbers, the ones in the title.
It gives you the full inventory, and it's astonishingly precise. Add it all up, and the universe comes out to about 5% ordinary matter. Everything you've ever seen, every star and planet and person, all of it, about 5%. Then roughly 27% dark matter, the invisible stuff holding the galaxies together, more than 5 times as much as the ordinary kind. And then the remaining piece, the biggest piece of all, about 68%, is something else entirely, which we haven't even met yet. It's called dark energy. Add the two dark pieces together, and you get about 95% of the universe that is nothing we understand. And there's the title of the whole thing.
95%. And 3 completely separate witnesses, the spinning galaxies, the colliding clusters, and this baby photo of the universe, all agree there's way more mass than the light can account for. Okay, I came in ready to be skeptical, and honestly, 3 independent methods landing on the same answer is exactly what should make me believe it.
That's the right reason to believe it, and I want to be precise about what it is. What those 3 witnesses prove, flatly, not we think, but prove, is that there is far more gravitating mass out there than the visible matter can account for. That's not in doubt. What they do not tell us is what the extra mass is made of. Hold that line firmly, because we're about to walk toward the edge. But first, I owe you the second shock. That 68%, the dark energy, comes from an even weirder story. The second shock. The universe is speeding up. For most of the 20th century, the big question was, the universe is expanding, everything flying apart from everything else. But by how much is that expansion slowing down? Because gravity pulls. All that matter should be putting the brakes on the expansion, gradually. Everyone was arguing about how hard the brakes were.
Right, that's the intuitive picture. You throw a ball up, gravity slows it. Throw the universe apart, gravity slows that. The debate is just whether it comes back down.
Exactly the right instinct. So in the 1990s, 2 rival teams set out to measure the slowdown. And the tool they used is lovely. A particular kind of exploding star, a type of supernova that always detonates at very close to the same true brightness. So it's a standard candle. If you know how bright it truly is, then how dim it looks tells you how far away it is. Measure them at different distances, compare with how fast they're receding, and you read off the history of the expansion, whether it was faster or slower in the past.
And let me guess, like every good story you've told me tonight, they went looking for one thing and found the opposite.
The exact opposite. Both teams, independently, in 1998, found that the distant supernovae were fainter than they should have been, farther away than expected. And the only way to make that work was almost unthinkable. The expansion of the universe isn't slowing down, it's speeding up. Something is pushing the universe apart harder and harder, overpowering the gravity of all that matter, trying to pull it back together. That something is what we named dark energy. It was so unexpected and so solid that it won the Nobel Prize in physics. in the year 2011 for the leaders of those two teams.
Okay, I need an analogy for what dark energy even is, because something pushing everything apart is doing a lot of work in that sentence.
You do, and this is one where I have to police my own words hardest. So let me give you the leading picture and immediately fence it. The simplest idea physicists have, the leading hypothesis, is that empty space isn't truly empty. That the vacuum itself, every cubic centimeter of nothing, carries a tiny constant amount of energy, and that energy has a gravitational effect that happens to be repulsive. It pushes outward. So as the universe grows and makes more empty space, there's more of this repulsion, and the expansion accelerates. Now the fences, and there are three. It is not a force between objects, like magnetism. It doesn't pull two things toward each other or push two things apart. It's a property of space itself. It is not antimatter, nothing to do with that, despite the anti-gravity nickname. And most important, that constant energy of empty space picture is our best guess, not something we've confirmed. We're about to see that we're not even sure it's constant. The honest horizon.
This is the part I've been waiting for all night, honestly, because you keep drawing that line between what's proved and what isn't. And now I want the real edge. We've got overwhelming evidence the dark matter is there, so we've caught some, right? We know what it is?
No. And this is the sentence I most need you to hear clearly, because it gets softened all the time. After decades of searching, with the most sensitive detectors human beings have ever built, we have not caught a single particle of dark matter. Not one. We know it's there. We do not know what it is. Let me show you what the hunt actually looks like. It's heroic, and it keeps coming up empty, both at once.
Okay, what does hunting for an invisible particle even look like?
The leading candidate for a long time has a clunky name. A WIMP. A weakly interacting massive particle. The idea is a heavy particle that ignores almost everything, but very rarely one drifts through your detector, bumps into the nucleus of an atom, and gives it the faintest possible nudge. So the experiment is, build something that can feel that nudge. The world leader right now is called LZ. It's a tank of about 10 tons of ultra-pure liquid xenon, sitting nearly a mile underground in a former gold mine in South Dakota.
Why a mile underground?
To hide from everything else. Up here on the surface, cosmic rays and background radiation are slamming into everything. It's a roar. That mile of rock shields the detector from almost all of it, so the tank sits in near-perfect quiet, waiting. Here's the analogy I like, and its limit. It's like trying to feel a single raindrop land on the surface of a completely still pond. And to have any hope, you've buried the pond a mile down so nothing else disturbs the water. But here's the limit of the analogy, and it's the whole point. After the most sensitive listening anyone has ever built, the pond has stayed still. The raindrop hasn't come. Their latest results, the best in the world, set records for how faint a signal they could have caught, and they caught nothing. They ran longer, pushed to lighter particles, and still, nothing.
And I have to ask the honest question. At what point is, we built the best detector ever and found nothing, just the universe telling us the WIMP isn't there?
That is precisely the right question, and I'm going to refuse to spin it in either direction, because both spins are dishonest. Spin 1. It's a failure. Dark matter's a fantasy. No, the three witnesses still stand. The mass is really there. Spin 2. We're on the verge, any day now. Also no, I have no idea if we're close. What a null result honestly does is narrow the possibilities. Every time LZ finds nothing, it rules out a whole range of what the WIMP could have been. That's real progress. It's just the hard, unglamorous kind. And there's a beautiful twist from their latest run. They've gotten so sensitive that they started detecting neutrinos streaming from the core of the Sun instead, which is a triumph but also an omen. Those neutrinos are the leading edge of a background that will eventually be very hard to see past. People call it the neutrino fog.
Is the WIMP the only candidate, or is the field putting all its eggs in one basket?
Not the only one. There's a very different candidate called the axion, an extremely light particle that came out of solving a completely separate puzzle in physics back in the 1970s and turned out to also be a great dark matter suspect. It's hunted in a totally different way. You sit a strong magnet in a special cavity and wait for an axion to convert into a single faint microwave photon. And the honest scorecard there is the same. A beautiful experiment called ADMX patiently scanning, and so far, nothing yet. And one clean fact, the dark matter almost certainly isn't anything already in our particle catalogue. The known particles, even the neutrinos we do have, are far too light and fast-moving to clump up and hold a galaxy together. So it's almost certainly something new. Our best hypothesis is a new particle. But I have to say hypothesis, not we know.
Here's the question that's been building then. If we've never caught the particle, how confident are we that it's even a particle? Could we just be wrong about gravity? Maybe there's no invisible stuff, and gravity just works differently out there than in my textbook.
Thank you for asking it, because that's not a crank question. It's a serious, living rival idea, and an honest guide has to put it on the table. It's called MOND, Modified Newtonian Dynamics. The proposal from a physicist named Milgram back in the 1980s is exactly what you said. Maybe there's no dark matter, and instead, when gravity gets extremely weak, below a certain tiny threshold of acceleration, way out at the edges of galaxies, it stops following Newton's law and gets a little stronger than it should. Tune that one threshold and you reproduce the flat rotation curves.
Wait, so it explains the exact thing we spent half the episode on, the flat curves?
It explains them beautifully. And I have to be fair here, because this is where MOND is genuinely impressive. With a single universal constant, it reproduces the rotation curves of thousands of individual galaxies, and it naturally predicts a tight relationship between how bright a galaxy is and how fast it spins. A pattern that, frankly, falls out of MOND more cleanly than it does out of dark matter. On the scale of single galaxies, MOND works strikingly well. So no, we cannot wave it away.
Then how do you choose between them? They can't both be right.
You go to the places where they disagree, and the big one is exactly the collision we talked about. Remember the bullet cluster, where the mass and the ordinary matter ended up in different places on the sky? That's MOND's hardest problem. If there's no invisible mass, and gravity just tracks the ordinary stuff, then the gravity should sit where the gas is. But it doesn't. The lensing shows the mass has moved on ahead, away from the gas. That's very hard for a pure modified gravity picture to explain, and it's a big part of why most physicists lean toward dark matter. And on the biggest scales, the clusters, that baby picture inventory, MOND struggles to account for all the mass, while dark matter fits it all together. So here's the honest state of it, and I'm not going to tie it in a bow. The majority view is that the totality of the evidence, especially the clusters and the cosmic background, favors dark matter. But no one has a particle in hand, so the door is not shut. And it's genuinely live. Just this year, there was a reanalysis of the bullet cluster, using sharp new images from the James Webb Telescope, arguing that maybe it can be squared with MOND after all. That's being argued about right now. The dark matter versus modified gravity question is not settled. It's open.
I really appreciate that you're not pretending it's decided. Okay, that's the dark matter side. Is the dark energy any better understood?
It's worse. Much worse. For dark matter, we at least know where it is and how much there is. We can map it. For dark energy, we essentially have one number, how much the vacuum pushes, and beyond that, we are close to clueless about what it actually is. And the deepest open question is almost embarrassingly basic. Is it constant? Is dark energy a fixed, unchanging energy of empty space, the simplest idea? Or is it something that has slowly changed over the history of the universe? We do not know.
And I'm guessing there's a new result that's stirring the pot, or you wouldn't have set it up that way.
There is, and this is where I have to be the most careful of the whole night, because it is so easy to oversell. There's a very new survey called DESI, mapping millions of galaxies to trace how the expansion changed over time. And when you combine its latest data with the other measurements, there's a hint, and I want that word to carry weight, a hint that dark energy might not be constant, that it may have been a little stronger in the past and a little weaker now. If that held up, it would be enormous. It would mean the simplest picture is wrong.
So how strong is the hint? Because hint, from you tonight, has meant very different things.
Let me give it to you in plain odds instead of jargon. Depending on exactly which datasets you fold together, it sits somewhere around a 1 in a few hundred chance of being a random statistical fluke. Now, that sounds compelling, but the bar physics holds itself to, before it will say the word discovery, is far, far higher than that. More like 1 chance in a few million. So this is nowhere near that bar. On top of that, the result wobbles depending on which combination of data you use, and there are real tensions between the different datasets that make serious people doubt it. So the honest framing is, it's a tantalizing hint. It's being argued about intensely right now, and it may simply melt away as more data comes in. Do not let anyone tell you dark energy has been shown to change. It hasn't. It might be. That's an open frontier. Live as we speak.
You know what's getting to me? Step back and look at the shape of the whole episode. We can weigh this stuff to the percent. 5, 27, 68. We're incredibly precise about how much of it there is, and we can't tell anyone what either of the big pieces actually is.
You've just put your finger on the thing I find most beautiful and most humbling about this whole subject, and I couldn't have said it better. We have taken a precise inventory of the universe, down to the percent, and we understand almost none of what's on the list. That's not a contradiction, it's the honest state of the field. Precise accounting, near total ignorance, sitting side by side. The 95% isn't a measure of how much we know, it's a measure of how much we've carefully weighed and still can't name.
So where does it go from here? Because you've been very good tonight about aims to and hopes to. I want the real, not the hype.
Then here's the real. There's a brand new observatory that just started up, and I love this. It's named for Vera Rubin, the woman whose flat curves we built this whole hour on. She passed away back in 2016, and they named it for her. It released its first images just this past summer, in 2025. It has an enormous camera, and over the coming decade, it aims to survey the entire southern sky, over and over, catching the faint lensing distortions from dark matter across huge stretches of the cosmos, and counting exploding stars to trace the expansion. It is one of our best hopes to map where the dark matter actually sits, and to pin down, finally, whether dark energy is constant or changing. But I want the tense exactly right. It aims to. It's a 10-year plan that has barely begun. It hasn't answered anything yet.
Let me try to say the whole horizon back to you the way you've taught me. Proved, believed, hoped, in separate hands. Proved. There's far more gravitating mass than the light can explain. 3 independent witnesses, not in doubt. Proved. The expansion of the universe is accelerating. That won a Nobel. Believed, but not proved, that the extra mass is some new particle. It's our best hypothesis, but every direct search has come up empty, and modifying gravity is still a live rival we can't rule out. and genuinely unknown, still hoped, what dark energy is, whether it's even constant. With one intriguing hint that might change everything, all might evaporate by next year.
That is a flawless summary, and holding those three in separate hands is the entire discipline of doing this honestly. So here's what I want you to carry out. Everything tonight started from one equation off your homework. V squared equals gm over r, and one stubborn fact, that a star at the edge of a galaxy refuses to slow down. That's it. That's the doorway. You didn't need graduate machinery to walk up to the single biggest unsolved problem in physics. You needed a first-year orbit equation and the nerve to take it seriously when the universe broke it.
One equation and the nerve to take it seriously. And the 95% is still out there, unnamed.
Still out there, unnamed, filling the room you're sitting in right now. Somebody is going to figure out what it is. There's no law that says it can't be someone who first felt the puzzle exactly where you're feeling it tonight. One honest step past the homework.
One honest step past the homework. I'll take it. Until next time, go look at a galaxy, and remember it's mostly something nobody has ever seen.